Hey guys, Ms. Gosling here. In this video, you're going to learn about resistance and resistivity. By the end of the video, you'll be able to determine the effect of area, length, and material on a conductor's resistance. And just so you'll know, when I say conductor, I mean wire. So let's go ahead and get started. So first of all, we should ask the question, do wires have resistance? So far, we've been assuming no, they don't. The only thing that we have to worry about with resistance in our circuits are resistors. However, wires do have resistance. So our answer here is yes. That resistance is small, but it is not insignificant. And so when we're doing our circuit experiments, our wire resistance is one of the main causes of systematic error in our circuit experiments. So in this video, we're going to talk about some strategies for minimizing wire resistance, and we'll also talk about what we can learn about resistance as a concept from resistance in wires. And to do that, I want to introduce the concept of resistivity, which we use the letter rho to represent. And rho looks kind of like a curly P, but sounds like an R in the Greek alphabet. And so that rho there is going to stand for resistivity, which is a quality of a material. So copper, for example, has the same resistivity as long as it's the same kind of copper. Similarly, all wires made of graphite are going to have the same resistivity, and so on and so forth. So the key thing is that resistivity is a quality of a material. So the quality of the material that the wire is made out of. And that resistivity is equal to the resistance of the wire, which you guys know. You guys have seen resistance before, times its cross-sectional area divided by its length. And I think that this equation is actually often more valuable if we rewrite it to solve for our resistance, because the resistivity, area, and length of the wire are the things that we are really changing, that we can change. So we can change its material, its area, its length, and we're going to measure the effect of those things on resistance. So when we rewrite this in terms of resistance, what we get is that our resistance is equal to our resistivity of our material times the length of our wire divided by its cross-sectional area. So with that, let's go ahead and look at some problems. So let's go ahead and look at our first example. What is the resistance of a 15-meter length of copper wire that is 2.0 meters in diameter? And the first thing that I'm going to add here, and this is just from looking it up, the material of copper has a resistivity of 1.68 times 10 to the negative 8th ohms times meters. And where those units come from will come through when we finish working through this problem. So now that I've translated from English to physics, let's go ahead and start by listing out our givens. So I know that my wire's length is 15.0 meters, and that its resistivity is 1.68 times 10 to the negative 8th ohms times meters. Finally, I know that its diameter is 2.0 meters. Therefore, its radius, which is my diameter over 2, is 1.0 meters. Which brings me to my unknown. And from this question, I can tell that what I'm looking for is my resistance, which is represented by capital R. Now, I'm going to go ahead and create my equation, which I am going to solve, for R algebraically before I plug anything in. So I know that my resistance is equal to rho times L over A, or my resistance is equal to rho times L over pi R squared, since my area is equal to pi R squared. Now that I have an equation that has just my givens and unknown, I'm ready to sub and solve. So resistance is equal to rho, so 1.68 times 10 to the negative 8th ohms times meters, times the length of my wire, which is 15.0 meters, divided by its cross-sectional area, which is pi times pi times r squared, or pi times 1.0 meters squared. Simplifying this out, I get that my resistance is equal to 8.0 times 10 to the negative 8th ohms. And what I want to show you guys here is the way that my units cancel out. So you'll notice, I'm going to erase this ohms for now. On top, the units I have ohms, and then I've got meters here and meters here, so ohms times meters squared. And then on the bottom, I have just my radius squared, so that's also measured in meters, which is going to be squared. You'll notice that my meters squared cancel out, giving me that my resistance is just in ohms, which we know is the units for resistance. So you guys can see from this problem now, not only how to solve one of these problems, but also where the units for resistivity come from. So with that, let's move on to one more example. A wire with a length L and an area A has a resistance R. What is the resistance of a wire of length 3L and area 2A? So what I'm going to do is I'm going to say that the resistance of my initial wire is given by rho L over A, and that the resistance of my second wire, which I'm going to call R2, is given by rho times 3L over 2A. And if I take the resistance of my first wire and divide by the resistance of my second wire, then I can find the ratio between them. So if I have rho L over A for my first wire, and I divide that by the resistance of my second wire, which is rho times 3L over 2A, what I'm going to do is I'm going to cancel out some L. I'm going to simplify and then start canceling things out. So simplifying my fraction, I have rho times L times 2A, because the denominator of the bottom fraction is going to go into the numerator of the top one. And then that is divided by rho times 3L times A, because the numerator of the fraction under that's being divided joins the denominator of the fraction on top. So here we can see now that it's easy to cancel. Rho, L, A, and A. So this means that the resistance of my first wire divided by the resistance of my second wire is equal to 2/3. Solving for R2, I find that the resistance of my new wire is 3/2 of the resistance of my, 3/2 of R, so 3/2 of the resistance of my first wire. And there you have it. We have done some dimensional analysis to figure out the relationship. We get to figure out how L and A affect the resistance of my wire, and how we can solve problems that have no numbers. So let's go ahead and talk takeaways. And I really only have one takeaway, and that is that my resistivity is directly proportional to area divided by length. And I want to just go ahead and remind you all as well of our equations. So again, our resistivity, rho, is equal to our resistance times our area divided by our length, or rewriting that, our resistance is equal to rho times L over A. So when the length of our wire increases, its resistance will also increase, and it's going to increase in a linear fashion. And when our area increases, our resistivity will decrease. So with that, it's now your turn to try solving some problems and exploring this concept a little bit more in a lab. So with that, I'm going to let you go. Best of luck and happy solving.